Morning, afternoon, everybody. Welcome, Math 3000. So the plan for today is to go over some existence proofs and disproof. We've been doing these things in some sense a little bit more informally, but we can kind of formalize the process today. I put up some exam materials. I can kind of talk about that towards the end of class if you want to start thinking about our first exam, which is coming up on Wednesday. So we can just touch maybe briefly on that a little bit today, just so you can have some stuff to do over the weekend to get ready for that. But we'll talk more about that on Monday. So on Monday, we'll mostly just review for the exam, and maybe we'll have some odds and ends to finish up with this worksheet. There is a homework assignment that is posted that I would recommend that you do before Monday, or definitely before the exam. So that assignment deals with proofs with functions and existence proofs and disproof. And this will all be on the exam. So I don't want to kind of minimize it by not collecting it, saying it's not important. It's just, I won't be able to give you feedback on it. So that's why I'm not collecting it. But definitely give those a shot. And Lindsay and I can give you guys a hand if you're having any trouble with those homework problems.
Is there going to be an answer key posted at all before the exam for the homework that we're not submitting?
Yeah. I'll
Okay.
post an answer key for that. Yeah.
Okay.
I won't post it right away because I think that it's good to try and suffer through it a little bit on your own and make some mistakes and not see exactly how to correct it and try and figure that out. But certainly at some point, if you can't figure it out, it's useful to see the solution. So yeah, I will post them probably sometime over the weekend. Any other questions? Okay, well, let's then begin with talking about existence proofs. So I'm working on worksheet 10 for today. So we have been doing some existence proofs. Mostly we've been focusing on how to prove a conditional statement is true. We've done some existence proofs. So let's just kind of formalize how that might go, talk about some different ways that we might want to do it. But if I want to prove an existence statement, then I just need to show that here is an example that shows that this thing is true. So with an existence theorem, we're not trying to claim something is true for all possible values. We just need to find one example that works. So for example, if we wanted to say there exists a real number x that satisfies this equation, one way that we can do it is actually construct an example. In other words, find a value of x that works. Does anyone know a value of x that might work here? Let's see. Can you guys hear me by any chance? You can. That's good because my computer is frozen. Well, that's good. This is moving. Okay, I guess I just can't play around with my computer. There we go. Okay, so I can see this. So does anyone see a solution for this? Yeah, I mean, it's a fifth degree polynomial. Yeah, so Bill has a suggestion for -1. That actually works. I don't think that would be particularly obvious to people unless you had some technology maybe to help you out with that. But if we wanted to prove this works, okay, here's a number -1. And when you're doing existence proofs, we don't just stop there. You should do the work for the reader to verify that this works. So that was something that came up on one of the previous homework assignments. You had a question like, show that there exist 4 subsets so that the intersection is distinct for all of these things. Some people gave me the existence of that, but didn't actually prove those things satisfied the condition. So just be sure you not only give the example, but then verify. I mean, it doesn't take much to verify that that works. So it's both, here's the thing, and here's the check that it works. So this would be an example of what's called a constructive proof, because we constructed an example, explicit example, the number -1. There are other types of existence proofs. Sometimes it might not be easy to come up with a concrete example, but it's actually easier to make a general argument. So here's how that might look for this one. Same statement. Here's an example of a non-constructive proof for this. So first, we're going to tell the reader like whether we think this is true or false, so that they know whether or not I'm going to try and show existence or I'm going to do a disproof. And so here we're just going to use the fact that this function is continuous. We've got, here's a value of x that makes f positive. Here's a value of x that makes f, sorry, one of these should be negative. I missed a negative sign here. That makes that negative. So the picture is when I plug in 0, I get 4. When I plug in -2, I get -46. And this function is continuous. So that means I have to be able to connect those 2 points without lifting my pen off the paper. So this means at some point in between, though we might not know exactly what that point is, it has to cross the x-axis. So this is saying in between, there has to be some value c in between 0 and -2. I don't know why I'm going this way. Sorry. -2 goes over here. Same idea, wrong point. That is when we're at -2, we know the value is negative. When we're at positive or at 0, we know the value is positive, and the graph has to connect them without going off the paper. So somewhere in between, which would be somewhere in here, there is some value c, which we happen to know is -1. But if we didn't know it was -1, at least we can just claim here that it has to exist. Does anyone know what theorem this is? Probably learned this in a calculus class and you might have forgotten it. Let's see. Begins with an I. Yeah, that's right. So yeah, someone's direct messaging me in. Mean value or intermediate value theorem. This would be the intermediate value theorem. That's right. So this is what's called the intermediate value theorem. Not expecting you guys to pop something like this off the top of your head, but just to give you an example about sometimes it actually might be preferred to do it this way if we actually can't solve it very easily. So this would be an example of a non-constructive proof because we haven't given the explicit example with the particular value for x. Any questions? So I would say, if you're going about these, they're both fine. These are probably a little bit easier to follow since it's, here's the thing, let's check it. It's a little bit nicer to have explicit examples given. So I might suggest like that's a good place to try and start. But if you get stuck, like I can't solve this equation, then you might want to think about more general ideas. Okay, are questions? Okay, so here are a couple of existence statements that we would want to prove. And so we'll get to some situations when these things are going to be false shortly. But if I'm proving this, the first thing that I would want to do is first say it's true. I guess here it's saying prove this, so maybe the assumption is that it's true. But on questions that say like decide whether this is true or false and then prove it or disprove it, it's good to indicate whether you think it's true or false. So this statement is true. And let's try a constructive proof, which means we're going to find values of A and B specifically, sorry, that are going to work for this. So in other words, we are going to state what they are and show that it actually is true. Any thoughts? Sorry, I had the chat set up so people could only chat me. You're welcome to chat everybody as well. But any thoughts on an example that could work here for A and B? So it definitely helps if you guys are trying to think about this. So I can see the people on the camera, they're thinking, I can see that. I don't know what people not on the camera are doing. That's fine. But you shouldn't just be waiting for somebody else to try and answer this. That's not going to really help things. So yeah, a couple people were suggesting the same thing actually. And they were suggesting, I got 2 messages that came in saying, okay, let's try 0 and 1 for these. And the question is that okay? And what we need to check is the only thing that these numbers need to satisfy is that they're real numbers. So I couldn't use like I and 2I or something like that. So 0 is a real number, 1 is a real number. Okay, here are 2 real numbers. Let's see if this is true. And we can see that both of these things are equal to 1. So maybe just to be really thorough with that. Okay, we check the left side, right? This is how we check to see whether an equation holds. We check the right side, the left side, make sure they're equal to each other. Any questions? And I think like as long as you set one of them equal to 0, then it really doesn't matter, right? You can pick any value for the other one. So, you know, when we're doing these existence proofs, you know, I think like if you're thinking about how I can prepare for the exam doing these, like you're not going to see this same exact example on the exam. So it's not really like, let's memorize this example and bust it out on the exam again, but more like, oh, you should be thinking about what are some general strategies that kind of work when we're doing existence proofs. So I think the more general you keep it, the more easily it's going to be able to apply to things that you do see on the exam. Okay, let me skip B and let's try and think about C first. So here we need to find 2 irrational numbers, A and B. Okay, so these can't be written as fractions, such that when we take A and raise it to the power of B, we actually do get something rational back. And just kind of general tip, as I was saying, you might want to think about things in general. This is going to apply for disproof too, is that you might not want to start with like the most complicated thing from the get-go. So you start with a basic example, maybe you'll get lucky and it works. If it doesn't work, the reason why it doesn't work might give you a hint as to how to fix it. Okay, and so for example, setting one of them equal to 0 is like a really basic thing to try and do, and that's totally legit, right? In fact, like the more basic your example is, the easier it's going to be for somebody to follow. So don't feel like you need to come up with a really complicated example. So one thing to keep in mind is like things like a equals 0, you know, sometimes these are special cases where things generally don't work, might work in a special case. Okay, and if it doesn't work, think about why not, and then how could I fix that? Is it possible to fix that? So with that in mind, when we're dealing with irrational numbers, there might not be a basic example because like I can't use 0, right? We need to have something irrational. So what are some common types of irrational numbers that we've seen? I was trying to think about that and see whether we can get some of these to work. Pi, yep, that's one. What's another really popular, what are some popular irrational numbers? E is another one, that's good. What else? Square root 2, yep, these are all the greatest hits of irrational numbers, yep. Think about something like that as well. These are all things that work. And so now start to think about, okay, these two things need to be irrational. And when I plug this in over here, I should get something rational back. So now what I want to think about are like which of these irrational numbers, when I raise them to powers, I might wind up with something that comes out to be rational. So in fact, we can pick 2 out of these and get it to work. Yeah, and so some chats are coming in. That's right. So we can use this notion that like E and natural log, they're inverses of each other and they undo each other. So I've got E and natural log of 2 as a suggestion. And in fact, which way would you want to line these up? So I'm going to set A to be I want it to be E or natural log of 2. So A, we're going to set to be E. Thank you. That came in on the chat. And then let's try B to be the natural log of 2. So then we've got E to the natural log of 2, which gives us 2 is rational. Great. Thanks for those suggestions. And so I think, you know, I won't necessarily ask you this exact question again, but kind of I think that the general idea here that's useful is, you know, let me think of the most basic irrational numbers that I've seen and think about, let me just list some of them and then think about, can I pick a pair of them that seem to satisfy this property? And these are not unique when you're coming up with these existence proofs, right? There are tons and tons of examples that we could have cooked up. Any questions? Okay, so maybe I'm gonna break us up into some groups to have you guys try and come up with this one. So here the idea is we've got 4 distinct real numbers, A, B, C, and D. These can be rational or irrational. So that exactly excuse me, exactly 4 out of these possible products, we've got 1, 2, 3, 4, 5, 6 different products. We want exactly 4 out of 6 to be irrational. So my hint here would be we don't want all of A, B, and C and D to be rational, or else all of those things are going to be rational. So the thing that you might want to start thinking about so when I say how many, I mean out of A, B, C, and D. So out of these 4 numbers that we pick, you might want to think about saying, well, we need this many of them to be rational, this many of them to be irrational, and then start to think about specific values that you could pick. So I would suggest here trying to do a constructive proof and give concrete examples for these values. Any questions? Yeah, so these are things that are definitely kind of helpful to bounce ideas off of people, because sometimes if you don't see it and somebody else does, it is really helpful to listen to their rationale about, here's how I kind of saw this problem. Okay, so rooms are open, and Lindsay and I will kind of just go in and pop in and see how the discussions are going. Thanks. I was just saying, it seems like the work went really well on these. There was some trial and some error, and that's normal on how this process goes. So just because it doesn't work doesn't mean it was a waste of time, as long as you kind of see why it didn't work and how you might correct it. So I'm just kind of curious. Let me just do it this way. We can use the whiteboard. You guys want to just kind of share maybe some of the examples that you came up with. So here was the group that Lindsay was working with. And try and remember, there was a group that Caden was in, and there was, it doesn't mean, Caden, you need to write. I'm just trying to organize who were the groups. And then, yeah, and then in the other room, there was, Jonathan was there. So I think, can you guys annotate this? I don't know if I need to change the settings. But if you don't mind, just, yeah, perfect. Just kind of writing out or typing out what your examples were.
I don't know how to write on.
Okay, I think Giselle, you were in this group, right? I think you were.
Yeah, can I?
Yeah, you can just
tell you.
I'll write it
Sorry.
out.
We said A was equal to.
Oh, I see. Someone got it in there.
To, oh yeah. Okay.
Cool.
I was like, I don't know what button to press.
Oh shoot. I think there's an undo. Okay. Sorry, you can ignore my A over there. Okay, so seems like one group had a 2 and square root of 2 and a 2 square root of 2, 1 and a -1. Yeah, and I think the one thing that came up is to be careful about this qualifier that these had to be distinct real numbers. So I know that there were some examples that people came up with where they used the same number, like square root of 2 and square root of 2. And that wasn't a legal thing to do. But you could tweak it by putting the 2 in front of the square root of 2. Now it's a different number, but it still has this nice property. When we multiply it, we get something rational back. So here was one with 2 real numbers over here, 2, excuse me, rational and 2 irrational. And kind of the key was that this is a pretty nice way of multiplying 2 irrational numbers to get something rational back. Did this one check out when you did all your products? So I think like A and B winds up being real and C and D winds up being real, and then all of the rest were irrational. Yeah, so that seems like it should work. This one used the same idea. They picked this pair and then they picked this pair, which have a similar, pairing between the square roots of 2, and this gives you as well AB being real, rational, and CD being rational. This is a pretty similar take off of this one over here, just using 3 and 1 instead of 1 and minus 1. This works out. I think this one over here is gonna give us too many. I think actually all of the products here would wind up being irrational, but if I do this, that might fix the problem. So now A times B would give me 1, and maybe something like this might fix it over here. So this would still have this property that when I multiply this times this, I get something rational. This times this gives me something rational. Any other products, right, would give me something irrational. Good. Any thoughts or questions that came up when you guys were talking about these? Okay, then I will clear this out. I'm going to share my iPad, but does anyone want me to hold off before I get rid of this whiteboard? Okay. Okay, so let's then move on into the other part of the reading that you guys did, which was on disproof, and this was in chapter 9. So now we want to, instead of proving that something is true, we want to verify that something is false. And I'll say that if you're trying to come up with a general plan for disproof, it might be nice to break this down into cases of like, when I'm trying to disprove this type of statement, here's a good general plan of attack. And I'll say the 3 types of statements that you typically want to disprove are conditional statements, there exist statements, and for all statements. So it might be useful to think about what's a general strategy that I can use when I'm trying to disprove a conditional statement, disprove an existence statement, and so on. We'll keep that kind of on the back burner while we're thinking about these. Okay, so yeah, the way that we can disprove a statement oftentimes would be to write out what the negation is and then actually show that the negation is true. So don't get this confused with proof by contradiction, where we start with the negation and we show the negation is false, right? That's the goal of proof by contradiction. When we're doing disproof, we're going to take the negation and we're actually going to show that the negation is true. So these are trickier problems because we're not told whether or not the statement is true or not. And sometimes that's the trickiest part. So these are saying prove or disprove, and if we have different techniques for proving and disproving things. And what you might want to think about here is sometimes if it's not clear what type of statement you're working with, is this a conditional, there exists, or for all statement, might be useful to write this as one of those types of statements. So does anyone see how we could rewrite this as a conditional statement? So what's the hypothesis here? What are we assuming? And then what are we claiming is going to follow from that assumption? So yeah, so I think you might have had an autocorrect there, right? For good being odd, that's right. So here the assumption, thank you for these suggestions, would be that we have two odd numbers, that's right. And then the sum of them is going to be even. So over here, we're going to say if x, or you can call them whatever you want, and y are odd, then x plus y is even. So that's another way that we could write this out as a conditional statement. And I think the advantage of this is that, you know, this is what we've been really working with up to now is conditional statements. And we have various proof techniques for them. So what do you guys think? True or false? Should we try and prove it or disprove it? And if you're unsure about it, here's a little kind of trick. It would be like, let's just try some things out, right? If, I think that's always a good step in these prove, disprove things. Just try examples and just be careful that you don't say, you know, that if I find one that works, sometimes that might be enough, sometimes that might not be enough. For an existence proof, finding one thing that works is enough. For something like this, it wouldn't be enough because we need to show that this is true for all odd numbers. So, you know, you can try like 3 plus 1, that's 4, 5 plus 3, that gives me 8. This seems to be working, right? But this isn't enough to prove it. Just be sure about that. So I would say if I'm kind of thinking about this, this gives me some indication that it's true. I would not need to see that with your work. That's more like scratch work. So if I wanted to write up a formal proof for this, okay, here we definitely need to say whether or not we think this is true or false. Since it's saying prove or disprove, that's not a proof right there. That's a start of a proof. So then we can come, this is a pretty hopefully familiar type of proof. We've been doing a lot of these even odd proofs. So I'm going to do this by direct proof. So let's suppose x and y are both odd. I don't know, it's very possible we've done this one already. Then what might be a reasonable next step after this statement?
Definitions.
Yeah, so what would that tell us then? What would be the definition of saying that x is odd?
It equals like 2k plus 1.
Yeah, and so one thing to just point out for the exam is, you know, I would definitely have a nice sheet of all of these definitions written out. And if I ask you, like, what is the definition of odd, and you quote the textbook, though you're not allowed to use the textbook during the exam, it's not plagiarizing when you write out a definition. So don't worry about like, oh, I need to write this a little bit differently. That's kind of the point of a definition, is we want it to be kind of concrete. Those are things that you would want to memorize. That's like the one thing that you really want to memorize are these definitions. Yep, so that means we can write them like that, and then what's a reasonable next step? Take the sum, that's right. So then this gives x plus y is equal to 2k plus 2m plus 2. And then hopefully you're getting good with these tricks, right? Hopefully I'm trying to show that it satisfies the definition of even. So I think one thing to make sure that you're keeping straight based on what we're doing today is like, when is it okay to just give one example and that's a sufficient proof, and when is it not okay? So when we're trying to prove for all conditional statements, we need to show more generally that this works for all possible things that satisfy the hypothesis. When we're doing an existence proof like we've been doing, those are situations where you just need to give one thing to prove that it exists. Any questions? Okay, so then let's try the next one, B, which is saying for every positive integer n squared plus 41n plus 41 is prime. So the first kind of thing to think about, again, this is like a prove or disprove. So again, you can try and I don't think it's a bad idea to start this process by like picking a positive integer like 1. That's the simplest positive integer that I could think about. This gives me 1 plus 41 plus 41. That gives me, did I do that right? 1 plus 41 plus 41. And that gives me 82, 83. Then we want to think about, is 83 a prime number or not? I'm going to think of a way to write 83 as a product of things other than 83 and itself. We got to vote for 83 is prime. That is prime, so that checks out. Sorry, where were we? And now we've got 2 plus 82. Here's where I need to do arithmetic carefully. So this gives me what, 123. That right? No, it's not right. What did I do wrong here? 2 squared is 4. which I believe is prime as well. We could check these, and we're starting to see that things are prime. But this is actually not true. And so, yeah, I think there is some something useful out of checking really basic cases. I think if you're stuck, that's like the first thing that I would try. But here's where you want to just hold off on, like, just because this works for some examples, we need to show that this works for all. And going through every positive integer, that's not a really efficient way to try and prove this. And in fact, this is not true. Does anyone think of a counter example? So if we want to disprove for every statement, right? When we negate a for all statement, we get an existence statement. So if I want to disprove a for all statement, it becomes an existence proof. Meaning I just need to give one counter example. Then we think about counter example here. Yeah, there you go. So n equals 41 is kind of a special prime number here, because if we plug in 41 for n, it's going to be a factor here. It's already a factor here, and it's going to be a factor over here. So that would take a really long time to get to that one. But if you were really thorough, I suppose if you have a computer, it's not as bad. But guess and check might not be the most efficient way to do this one, but looking at the structure of the expression here might be a more useful strategy. So that's what's going on with that one, right? 41 is kind of a special prime number because when I plug that in, now we get 41 is a factor of each term in that sum. So it can't be prime because 41 is a factor of that number. Any questions? Okay, so just to see how we could write this up more formally, we could just say that this statement is false. We're going to show that it's false by providing a counterexample. And our counterexample is let's let n equal 41. That gives us a not prime number. So here, the kind of trick would be like any multiple of 41 would be successful there, would have worked. Any questions? Does it make sense if we want to disprove all for every statement that this becomes therefore an existence proof? And I think just for some practice on these, and as well as just like practice negating things, is if you're kind of stuck on the step, like I'm pretty convinced this is false, but I'm not quite sure where to go after coming to that conclusion, it might be nice to just kind of negate the original statement. And it might, if it's helpful for you, you can write that symbolically and then negate it that way. But just remember, when we negate all for every statement, what we're going to get is there exists a positive integer such that the negation is true. In other words, n squared plus 41n plus 41 is not prime. So this is where this work that we did earlier in the semester, like being careful about how we negate statements is really, could be really useful in this process. So that kind of goes back to over here. That if I want to disprove a for all, then we have an existence statement. Any questions?
I have a quick question.
Yeah.
For if you're trying to prove an example of, like, for this situation, n was equal to 41, but like, you know, we tested at the beginning, we couldn't really determine if the statement was true or not. Is there like a quicker method or some sort of technique that we would use to get to, you know, like, there's no way, like, I mean, generally it's hard to determine that n was equal to 41, but do you know what I'm saying?
Yeah, I mean, I think that the more strategies, the more general your strategies are, probably the easier they're going to be to apply to different things. So one strategy is guess and check, sort of, right? Just try out some things. And I think that's always a good step. If you're never sure what to do, just try something out and see what happens. But this is a case where you don't want to just do that. This might lend you, like, I'm going to check the first 40 things and you would get 40 things that are prime. That might be really convincing. So I think the other general thing that you might want to look at here, and it's hard to like come up with, here's a plan of attack that's always going to work, but just kind of looking at the structure of the expression and trying to think about, is there kind of a really special n that I can pick that's going to make this whole thing composite? And so it might not be evident, but the fact that you see, like, here's some interesting structure in this expression. I see a 41 here and I see a 41 here. That might make me think 41 is special, and just try it out. And then you can see, see that is not prime. So sometimes, you know, looking at the structure of the expression might help you think, well, maybe there's like a special case that might be worth checking.
Okay, sounds good.
Yeah. Okay, so want to take a look at E. I just made these notes so I know which ones we want to do together. And then next time, next class, I think we can come back and practice more of these together, and before we start to get into the generalities of the exam. Well, let's take a look at E, which is an existence statement. So now we want to try and think about whether this is true or not. If it's true, we need one example. If it's not true, we need to think about how we can disprove an existence statement. And again, you know, here you could try some guess and check. So we're going to pick two prime numbers. Their difference gives us 97. And you could try out a bunch of pairs of prime numbers, trying to think of things that are going to give us 97, but you won't get successful. So let me just say, without going into all the details, you could try some examples. Okay, but none of them are going to work. So I think after thinking about it for a couple minutes and you can't think of something that works, you might want it. That would be a good time to like, let's switch strategies, and instead of trying to show that that one of these exists, let me try and think about, can I prove that it doesn't exist? So so if I want to negate this, so that's how disproof goes. We state the negation and then we show that the negation is true. So what would the negation of that statement be?
Would be for all prime numbers.
Yep, so we change that there exists to for all prime numbers, P and Q.
And then that expression is not equal to 97.
That's right.
Negate it, yeah.
So we change the there exists to or for all, and then we negate the end of that. And when we're proving things, remember, like every for all statement can be rewritten as a conditional statement, and that's useful to do because we have certain techniques for proving conditional things. So this is equivalent to saying if P and Q are prime, so just to kind of follow what my logic might be on a problem like this is, let me first try some examples. They don't work. So next, let me think about what's the negation of this statement, and does that seem true? So we write the negation of this, we get a for all statement. For all statements can be rewritten as conditional statements, and the advantage of that is that's really what we prove in mathematics most of the time, are conditional statements. So here we're going to say the original statement is false. We're going to show this is false by proving its negation is true. I think this little plan, describing your plan initially, really helps me or whomever is reading things. First of all, I want to know whether you think it's true or false. Then explain to me how you're going to show that, whether it's true or false. So here's the statement that we want to show is true. And I'm going to prove this using contrapositive. Why do you think contrapositive might be a good proof technique here? So we've got like a conclusion here, which is a not equal sign. Yeah, and so it might be easier to work with things that we assume are equal to something. So sometimes when you see these not equal to things, you might want to think about the contrapositive that would make things equal, and it's a little bit easier to work with things that we know are equal. So I'm going to explain how exactly I'm going to prove that statement. I'm going to use that by contrapositive. So we assume the opposite, P minus Q, is equal to 97, and we want to show the negation of the hypothesis. So remember, the hypothesis is an and statement. So the opposite of saying P and Q are prime is not saying both P and Q are not prime, right? But rather just as long as one of them is not prime, that's going to be enough. Okay, so let me see. We've got 2 minutes. So let me, and we'll come back to this. We'll pick up here. Since I do want to just maybe make a couple of comments about the exam before we stop for today. We only got a couple minutes. So yeah, it's always good to leave you like with a cliffhanger. Back in the day before like you can binge watch an entire series in like one day, we actually had to wait like a week before the next episode came. They would always leave us with a cliffhanger. So this is a cliffhanger. So let me take a look at our website. And I added a little section about the exam. Don't get excited about these links. They are not working yet. Well, they are, but if you click on it, you'll just see, okay, good. This is locked until about 11 o'clock on exam day. So just to know, like you'll get access to the documents over here. So everything will be administered in Canvas. Here's a link to where I've been posting additional practice problems. So if you want to practice some problems that you haven't already solved on homework, that's always a good thing to try and do. And in addition to that, I put an exam 1 info sheet. So over here, you can kind of, this is like what the first page of the exam is going to look like, just so you know what you can and can't use during the exam. So give that a read. The exam is going to cover everything up to and including what we talk about today on this last worksheet. So I would say I just put some motivating questions that you might want to think about as you're going through the worksheets to collect your thoughts. But I would say, you know, overall, the main thing that you might want to think about doing over the weekend would be thinking about like, let me get a list of all of the definitions and let me state them really, really clearly. And it's okay if you restate those things on the exam. I'm looking for very clear and direct definitions. So that's fine. The second thing you might want to think about are like, what are all of the general proof techniques that we've had? So just summarize, here's how direct proof works, contrapositive, contradiction. Here's how we prove subsets. Here's how we prove set equality. Here's how we prove injectivity. So I would just go through the different general proof techniques that we've had, not get too specific, and just try and write out in general, here's how this proof technique works. And you might want to put some little hints like, hey, contrapositive seems to be a good idea when we're working with these types of statements. Direct proof, that seemed to work when we were dealing with these types of statements. So those are some things that you might want to reflect on. I know we're out of time, but I don't want to put you on the spot, Lindsay, but if you have something to add, since, you know, I'm coming at it from an instructor point of view, Lindsay has actually taken the exams. I don't know, do you have any additional thoughts on that, Lindsay?
Yeah, absolutely. Something that really helped me last semester was there's obviously the multiple choice portion that you have. Is it 20 minutes at the beginning of the?
Yeah, like 25 minutes. Uh-oh. I think you cut out, Lindsay. Can you guys hear Lindsay? Oh.
Hello.
No.
Can you hear me now?
Yes, we can.
Okay. I can either just make an announcement if my internet is cutting out on the Canvas page, or I can try again. Up to
Okay,
you.
well, we're hearing you now. Let's try one more time.
Okay, perfect. Okay, so you have the multiple choice section that you have the first 20 minutes of the exam to take, and then you have that free response section. And I would recommend trying to save as much time as possible for that free response section. And so as confident as you can be in the like multiple choice quizzes that we've taken at the beginning of class and that sort of information, I would recommend relying on your notes as little as possible for that section to leave time for you to really figure out the proofs that might be there, or just to kind of problem solve on the free response section. And then for that free response section, doing those practice problems that Adam suggested, and yeah, making that cheat sheet with your definitions is huge, and knowing just how to approach each of the different proof techniques is really what I did last semester for tests.
Okay, thanks. Yeah, so I would, encourage you guys to start organizing your thoughts over the weekend. We'll talk about the exam on Monday in more detail. So if you have some questions, bring them with you. And yeah, you're welcome to reach out to myself or Lindsay if you're looking for more suggestions about preparing for the exam. Feel free. I've got office hours tomorrow morning, 10:30 to 11:30. And yeah, so if I don't see you before next Monday, have a nice weekend, and yeah, get working on that homework assignment to get you ready for the exam. Okay, thanks. Have a nice weekend, everyone.
Thank you.
Thanks, guys.